Yeah, thanks to the invitation and thanks to the award committee for selecting our work. It's really an honor to stand here to talk about this topic. So this work is co-authored by Professor Arnold Janssen, Professor Winan, and me back to 2017. And since then, we have seen a very rapid growth in these directions with a lot of interesting and exciting developments. So it becomes a bit challenging to me uh, when I prepare the material because there are so many recent progress and it's very fast growing and uh, and I finally decided to I finally decided the following plan for today's talk. So I will first talk about the background, why back to that time we are so interested in using deep learning to solving high dimensional equations, mainly due to the intrinsic difficulty. And then I try to introduce a general framework to think about how to design deep neural based algorithms for solving PDEs. So as you will see, this framework is very general, basically incorporating various existing algorithms. And then I will mainly focus on the first step of this framework, choosing suitable formulations of the PDEs choose the suitable formulation for solving high-dimensional PDEs. And the two main examples, one is based on the backward stochastic differential equations proposed in our awarded paper, and another is the classical variational formulation. And the last, I want to conclude with some future directions, at least in my personal opinion, that are of like significant scientific computing interest in the recent years and in the near future. Okay, so yeah, so I will start with the background. So a computational approach has been a third pillar in our study for science and engineering, especially when analytical approach or experimental approaches are unavailable. Especially the numerical methods for partial differential equations has completely changed our ways of doing science and engineering. So they can find numerous applications in a lot of disciplines, including structure analysis, fluid dynamics, optics, control of flight vehicles or satellites, and uh, and uh, and beyond these regimes where we have so far at least we have developed very reliable numerical methods for solving PDEs. There are another regime of PDEs, the so-called high-dimensional PDEs, where we still suffer some essential difficulty, which I will talk in a minute. So before that, I just want to list like two typical examples of high-dimensional PDEs we will encounter in our scientific computing. The first one is the famous Schrodinger equation. So here U denotes the wave functions. And the t is the time, x is the location of the electrons if we consider our 3D real world. So if you can solve the so-called wave functions, you can get all the information of the quantum systems of your interest. So here x denotes the locations of your electrons positions. So even when you consider a single water molecule, okay, there are 10 electrons. The dimension of the whole Schrodinger equation is already 30. And the second one is the Jacobi-Bellman equations arising in a lot of disciplines. One discipline is the optimal stochastic control or coming from the dynamic programming. So here the function U is the so-called value function in dynamic programming, and the X denotes your state variables. So the dimension of the PDE is the number of the state variables, and in a lot of optimal control problems in real world or some financial world or others, you can easily have number of you can easily have state variables of dimension 10, 100, or even higher. And why solving this kind of high-dimensional PDEs is difficult. So let me use the Poisson equations to explain it briefly. So suppose you have Poisson equations in one dimensions over the interval from 0 to 1. Then you pick if you use find difference method, you pick a large enough integer capital N and define the graded size h equals 1 over n. Then you can use the classical central difference to approximate the second order derivative, and then you have a linear systems of size n plus 1 to approximate the function the unknown solution values over these grids. And you can do the same thing if you have Poisson equations in the two-dimension case. You have the find difference, which connects the node in the center to the 4 neighboring points. And so for both 1D, 2D, and arbitrary dimensional Poisson equations, numerical analysis tell us the obtained numerical solutions from solving these linear systems will have error of order h squared. Okay, so what's the implication of this result? Recall that h equals 1 over n in our definition. So if you want to have a solution with error of order h squared, in the one-dimensional case, you need to solve a system of size order n. In the two-dimensional case, you need to solve a system size of order n squared, and etc. and etc. If you have d-dimensional problems, then that means you need to solve a system of order n to the power of d. Okay, so that's the famous phenomenon called the curse of dimensionality. If you have n nodes in each dimension, and in order to achieve a solution with error h squared, as the dimension variable d grows, the computational cost is n to the power of d, which grows exponentially with respect to d. So you cannot imagine solving problems in such a way when d equals like 10 or 100. Just to give you a concrete idea, say if you want to reduce the error by a factor of 4, according to the h squared error, then you have to grow the system size with a factor of 2 to the power of d. Okay, when d equals 1 or 2, it's very reasonable, but when d is large, it's beyond our computational power. And this kind of curse dimensionality phenomena exists not only in the find difference method I just explained, but also in a lot of other numerical methods for PDEs, such as find element method, spectral method, etc. So in a lot of problems, you will see, okay, the problems we can really handle, the dimension is maybe 3 or 5, roughly. And this phenomenon also exists in a lot of other scientific computing problems whenever they involve a lot of state variables. The deep-rooted reason is related to the fact that to approximate high-dimensional functions with traditional methods, with like polynomials, wavelets, we need exponentially many basis functions. Okay, that's the root for this phenomena. And okay, we all know that within the 10 years, like deep learning has revolutionized the whole computational world. And if we take a mathematical perspective, okay, one major task that deep neural networks are good at is general function approximation. Okay, so if I use the supervised learning task as example, we have a data set which has a pair of x and y, where x is the input and y is the output of function f star. So given data set, the supervised learning task in deep learning is to find or approximate the function f star, which can be high dimensional. Okay, say if okay, so there seems a lag between laptop and display. So say the classical CIFAR 10 classification problems, the input of the function is image of RGB. So its dimension is like 3072, and the output is 10 categories. So from a classical numerical analysis perspective, we cannot imagine approximating such a high-dimensional functions. But apparently, deep neural networks can do something meaningful for these high-dimensional functions with the so-called neural networks design. So this is exactly what we have designed in scientific computing for a long time. Okay, we hope we can have something like polynomials, but works in high dimensions. And that's why we got interested back to 2017, trying to using machine learning to solve, or especially deep learning to solve high-dimensional PDEs. And in terms of how deep neural network works, it consists of a few key elements. First, you need to design a network in terms of a representation. So the key feature of deep neural networks is a composition between a lot of basic linear transformations and the nonlinear activation functions denoted by sigma. And then once you choose a representation form of networks, you can construct optimization problems. So either based on the data set you have or respect to underlying distributions. So here I'm using a theta to denote all the parameters. And given this optimization, then you can use the so-called stochastic gradient descent or its variance to optimize to these problems to find the near optimal parameters. So that's the paradigm of how deep neural networks works for the classical supervised learning problem tasks. And the key questions we were facing is that how can we transfer this kind of paradigm to solving PDEs? So now I'm going to introduce the framework as a general framework to consider solving PDEs using neural networks. It consists of 4 steps. The first steps, as you have seen in the previous slide, in order to train a network, you have to construct certain optimization problems. So the first step means you have to find, you need to choose a formulation that is equivalent to the PDE and write down functional optimization problems to your PDE solving problems. And the second, with these functional optimization problems, taking any function as input, then you would like to consider the neural network's approximation to design the so-called candidate or trial function space. So in this step, you will use the architecture or representation of deep networks. And the third step, the functional to be optimized may still difficult to compute if you want to have a high accuracy. So we have to introduce certain approximation of this objective functional with certain numerical quadrature. So this is a topic in a classical topic in the traditional numerical analysis. And then after these 3 steps, you finally have a finite dimensional optimization problems. You can use the stochastic gradient descent to optimize the functionals and hopefully solve the original PDE. Okay. So this is the overline of the general framework I want to talk about today. And in the later part, I will mainly focus on the first step, especially how we choose proper formulations that is suitable for high-dimensional PDEs and construct a certain functional optimization objective. But before I go into details, let me take a simple example to show you how to interpret this general framework. So you may have heard of the physics informed neural network, which is arguably perhaps the simplest method in this regime. So suppose we want to solve a second-order neural network. In the first step, we needed to find a formulation. So the simplest formulation is just a strong formulation or least square formulation. If the equation equals to 0, then that means if we take the square and the integral over all the possible points, this objective should also be 0. And if we want to ensure that boundary conditions is satisfied, then we can construct a similar term, and then we just combine these 2 terms together. So if we can find a u minimize this function, at least a square functional, then we may think, okay, this u is the solution of the PDE. So that's a strong formulation. And then the natural thing, the second step is to use a neural network to approximate all the possible function you want to search. So you use a neural network with parameter theta to find the best solutions over these families. So that's the second step. And the third step, the original objective is integral over all the dx. So you have to use certain numerical quadrature to discretize that integral. Okay, the simplest method is the Monte Carlo. So you just sample n1 and n2 points in the whole domain omega and the boundary. Then you get a finite data version objective, and finally you can just use the standard gradient descent or other methods to compute the gradient and optimize the parameter theta. So that's how physics in formulator works.
One of the problems because of dimensionality is that it seems like you have to use an integral, so I guess you sample instead of discretizing, but that could have also done it in the original.
Oh, you mean the how many data points you need for the integral? Okay, that's a very good question. So for the integral, if we use Monte Carlo method, we know that the convergence rate is 1 over square root of n for Monte Carlo integration, which is kind of like independent of dimension. So Monte Carlo integration is kind of one of a few tools we have for high dimensions, which do not suffer from the curse of rationality. So this part is not so so pessimistic. Check the key part. The key difficulty is how can we find a good numerical representation or optimize to find the parameters. Okay, yeah. So this is an example how this general framework how it works and how you can think about algorithms. Omega can be. Yeah, that's a very good question. So in general, okay, in terms of formulations, the omega can be a very arbitrary shape. So for example, if you want to solve PDE over sphere, then you need to be careful how to sample the calculation points over the domain. Yeah, so that's the issue you need to come in the third step. But as I said, this is just a classical topic in numerical analysis. Yeah, thanks for the question. Okay. Yeah, so this is just one example of how the PIN works for the simple one-dimensional equations. So it gave us a different way to solve the PDEs using the learning framework. And then now I will go to the first example of the Deep BSDE method proposed in our paper. So why we will choose the so-called parabolic functions? Then before that, let's first consider the linear PDEs. Okay, so this PDE is the parabolic type of second order. You can see here that the time derivative and the Laplacian have the same sign. So we specify the terminal conditions, and we want to know the solutions at the initial time. And this PDE is called linear because the driving force F does not depend on U. And this is actually a very special type of PDE. Okay, I will say this is one of the few PDEs we can solve before machine learning or deep learning in high dimensions. Why? Because we have the famous Feynman-Katz formula. If we consider a forward process xt, where the drift mu comes from the drift term in the original PDE, and dwt is the Brownian motion, and then we consider another process where we evaluate the unknown solution, a PDE solution u at t and xt. Okay, then you can apply the classical Ito's formula to write down the dynamical process of du dut xt, and then all these terms coincide very well with the PDE. If you use the PDE conditions, you can write the process as such a process where drift is minus f, and the coefficient in the diffusion is gradient of u. Okay, so this kind of process of u is called a backward stochastic differential equations because we know its terminal value at capital T, and we want to know its value at initial time. And if you take the martingale property of the SDE, take expectation on both sides, then you can have a final expiration of the PDE solution U in such a form. So if you take a further look of this form, you can see the solution U is expressed in terms of expectation. So back to my first answer, we can use Monte Carlo to approximate this expectation. We just need to simulate. Suppose we want to know the solution at t equals 0 and a certain point x. we just simulate a lot of forward process starting from that initial point, and then we get all the paths, and we just evaluate this Monte Carlo over all the sampled process. Okay, so this convergence rate is 1 over square root of n, where n is the number of passes. So this is why we can overcome the curse of generality. And another nice feature of this method is that this is a local parallel method. It's not long. It's unlike classical global method. In order to get the PD solutions, you have to solve the unknowns over all the grid of points. So here, in order to get the value of at a certain point, you just simulate a lot of passes starting that point. That which is enough to give you the information of the P. Okay. Now let's try to solve the problems in a more general form, which we find necessary in a lot of applications. So here, the PD becomes semi-linear because the F becomes nonlinear depending on U and the gradient of U. So if you, okay, I see. If you use the same procedure or introduced above, consider the same forward process and consider the same backward process U. Okay, you can rewrite the solution U as such expectation. Okay, it's still expectation, but the bad news is that in order to evaluate this expectation, you need to know the values of U and the gradient of U over the passes. So, but this is something we don't know and we want to solve. So it becomes a chicken and egg problems. How to find a solution through this kind of formula. But this formulation of Feynman-Katz formula is very useful for us to construct a learning-based method. So that's the key point of our paper. So if we rename our process UTXT as YT, and suppose we know, of course, we know Y0 equals, assume Y0 equals U at 0 and X0, and ZT is a gradient process, then we can consider the forward process for both XT and YT. So the process becomes forward because we assume we assume certain Y0 and the driving part ZT. And then the boundary condition, the terminal conditions is YT equals GXT. So in that sense, we can reformulate the original PDE problems in such optimization or variational problems. We want to find Y0 and the ZT such that under the following true forward dynamics, the final GXT is always YT. So that's the main idea of the formulation. It rewrites the original PDE solving problems into a variational problems following the logic of the Feynman-Katz formula. And this formulation has a few good features. First, we know the PDE solutions is a minimizer of that formulation because it's just a zero, and by the theory of the BSDE, we can show the minimizer is unique. So combine these 2 points, we know the minimizer for this formulation is a PDE solution. So this is a correct formulation. And more nicely, numerically, we can show, theoretically, we can show an approximate minimizer for the PDE problems is an approximate PDE solution. So which means that the whole formulation is stable. And another nice point of this formulation is just what I mentioned in the previous slide. So in order to solve the solutions at a certain point, you just need to simulate the process for starting from that point. Then you optimize this formulation. You only need to optimize unknown Y0 and ZT that is relevant to the points you are interested. So this is a parallel and local method. Otherwise, if you use like other classical method, in order to sense the boundary conditions or terminal time conditions, you have to sweep all the points, which is very costly for high-dimensional case. Okay, so that's the first step of the whole general framework. Then we can use the same idea to implement the whole algorithms. With this formulation, we first apply certain we first apply certain time discretization to resolve the continuous dynamics. So in our paper, we just use the simple forward order discretization, and then in order to formulate to represent these unknown functions y0 and zt, we use certain neural networks. So that's just the second step, and the third step, representation and discretization in my general framework. And then we have a concrete deep learning problems to optimize. And if we optimize these things, and to find certain optimal parameters, we expect it to give us an approximate solution to the original PDE. So here is a schematic plot of how the Deep BSDE method works. So you can see the x0 is the starting point, the point you want to solve the PDE, and you can think about the Brownian simulate the Brownian motion as such kind of data, because it gives you the forward dynamics of the DXT, the SDE. Then we would like to have a neural network to approximate the function maps between the x0 and the unknown gradient. And with the function approximation, with approximate gradient, then we can define the forward dynamics of u until terminal time. And if we have the u at the terminal time, then we can use the least square formulation to define our loss functions. So this is our loss functions. This is our data, and the parameters in the neutrals are something we want to optimize for this. And the whole computational graph is differentiable, so we can take the gradient descent to iteratively optimize the parameters. So that's the whole idea of the Deep BSDE method. If you are interested, so the code is open sourced on my GitHub. And yeah, so I just want to return to the first point I mentioned. So this formulation is turned out to be stable in the following sense. We can have a posterior error estimate for the whole method. So suppose we have a time discretization scheme denoted by pi, where h is the graded size, a discretization graded size over the time interval. Under certain regularity assumptions, we can show that there exists a constant c independent of dimension d and the graded size h, such that for sufficient small h, we have the following estimate. So in this inequality, the left-hand side is the error of yt, which means the solution error of the solution u, and the second term is the error of zt, which means the error of gradient of solution u over time. And the whole errors can be bounded by the constant c times two terms, where h is the time mesh size, and the second term is just our loss function. Okay, so this is the classical posterior type of error analysis, which means if we have a refined enough time mesh and we find the loss function is small enough, then we can claim the approximate solutions is accurate enough. Okay, so here is a numerical example in our original paper regarding a 100-dimensional Hamilton-Jacobi-Bellman equation derived from a classical linear quadratic Gaussian control problems. So for this 100-dimensional problems, so we can, in order to find the solution at a single point, a laptop can finish it within 5 minutes with a final error of 0.17%. And the algorithm is robust for different parameters. So here I'm just showing the robustness with different parameters in the PDEs. If we change the values of if we change the values of lambda in the PDEs with the same parameters and the same networks, we can always find the solution values of high accuracy in these PDEs. Okay, so we have seen some working examples showing the formulation and the success of the Deep BSDE method. You may have one questions. Okay, so here I'm saying that we can use deep neural networks to approximate high-dimensional functions, and the PDE solutions themselves are also high-dimensional functions. So why don't we just use deep networks to directly approximate the PDE solution instead of approximating the gradient and y0 as I proposed in the BSDE part? Okay, yes, we can, because this is exactly the idea of the physics-informed network I mentioned at the beginning. But the key point I want to make here is that we can achieve better results when we exploit the mathematical structure of the original parabolic PDE problems. So that's why I want to talk about the formulation, because I think even with a very powerful computational tools like deep networks, the choice of formulation still matches. So here is a comparison of of the strong formulation or least square formulation and the BSD formulation over a second order type parabolic PDEs. So you can see as we increase the dimension over the x-axis, the error of the solutions based on the BSD formulation is always lower than the strong formulation, and moreover, the note that in order to use the strong formulation to solve the PDE, you have to evaluate the hashing of the neural networks, which is in general very expensive. But in our BSD method, okay, that part is approximated by the Brownian motion, so we do not need to evaluate the hashing, which can make our algorithms much faster than the strong formulation based network. Strong formulation based algorithms. Okay, so here I just mentioned there are some recent attempts trying to alleviate this difficulty for the strong formulation or physics informed network, and because it is it's still a very general idea, so it's still an active area of research, I think. Okay, so I will move to the second example, the variational formulation. Okay, so this is a very classical formulation we used when in the classical numerical method when we solve like low-dimensional PDEs. Basically, in many physical problems, the solution is related to certain minimization or maximization. Okay, in physics, you may have heard the so-called Fermat's principle or principle of least action. Okay, like the light will follow the path of the shortest optical length connecting two points. Okay, so if I use the Poisson equation as example, suppose this is the Poisson equation we want to solve for a general domain omega. You can construct the following function of J, where is 1/2 times the norm of the gradient minus fx vx, and you specify the admissible set K for all the functions that satisfying the given boundary conditions. Okay, then mathematically we can prove if U is the Poisson equation solutions, then U must be the minimizer of this function optimization problems. Okay, and the vice versa also holds. So this is what I mean by the formulation. And naturally, you can see this formulation is very compatible with the deep learning based framework for solving PDEs, because you can just use neural networks to represent this admissible set. Okay, so under the deep learning framework, okay, it's called deep reads algorithms proposed by Wina and Yu in 2018. So the key idea is just to solve these functional optimization problems under this constraint and use neural networks to represent this unknown solution U. And in practice, people will consider a relaxed version, treating the constraint as a penalty to facilitate the optimization. So then you can again use Monte Carlo method to approximate the integral in this objective and use stochastic gradient descent to optimize parameters. Okay, so here I just borrow the numerical example from a paper where you want to solving a Poisson equations with an interval removed from the whole square. So that the removed interval will create a certain corner singularity at the origin, and you can see that the neural networks are able to find a good approximation for these kind of solutions. Okay, so that's the true example. I think for this case, it is slower than the classical method because it's a 2D case. But in the original paper, they also show the results for 5D and 10D problems. I think then the classical method cannot afford to solve the equations. Yeah, good questions. So here it's just a 2D example showing the correctness of the solutions. But in the 2D case, there's no advantage for this thing compared to the classical method. Yeah, thanks for the question. Okay, yeah, so that's the two main examples I want to mention when you consider designing high dimension deep neural network based algorithms for high dimensional PDEs, and you can see both methods naturally fits the general framework I introduced in the second section. And as a summary, so you can see the key point is that, okay, which we find over a lot of works over the past years, is that for a long time, solving high-dimensional PDEs will suffer from the conventionality, and now deep learning provides us some efficient tools to overcome this difficulty. So far, we do not have a very satisfying understanding why deep networks sometimes works. Because you can easily think there are certain difficult high-dimensional PDEs beyond this kind of approximation of deep networks, but at least for certain PDEs, possibly with some intrinsic low dimensions, deep networks turns out to be a very useful tools for solving. If you are interested, we have a review paper on this topic, covering some classical nonlinear Monte Carlo methods and machine learning based algorithms. So yeah, here I just want to repeat the whole step, because I think it's a very general framework to consider or understand all the existing algorithms. So in the first step, you need to choose a formulation that is equivalent to the PD and write down the corresponding functional optimization problems. Then you use deep network-based approximation to design your candidate function space. That's the representation part. Then you approximate the objective functions with some numerical quadrature. And finally, you solve the final optimization problems with some optimizers. Okay, so in all four steps, there are a lot of unknown questions or open questions you can try to improve, like the sampling part for the third step, or the optimization part for the fourth step. But today I mainly talk about the importance of the formulation for the first step. Okay, and yeah, I still have a few minutes. Then I want to talk about like two directions I personally think are very interested right now, which I think will be potentially important and useful to develop machine learning based algorithms. So first direction is the ground state computation of Schrodinger equations. So the ground state means a quantum mechanical system that is stationary of the lowest energy. So mathematically, we have a very nice formulation for the solutions we are looking for. You can see that the formulation is very similar to the Riesz formulation I mentioned in the previous slide. Okay, we just have a normalization constant because it's kind of a normalization conditions for the wave functions. And if you discretize that whole systems, you can think it is equivalent to the smallest eigenvalue problems of linear systems. And solving the ground state is one of the central problems in quantum physics and quantum chemistry, depending on how you interpret the meaning of x. And but in both cases, the dimension of x is proportional to the system size, which can be very large. And even before the popularity of the deep learning, okay, computational chemists or computational physicists have been using this formulation to design the so-called variational Monte Carlo method to find the ground state. Okay, you will see the variational Monte Carlo method is again belonging to the general framework. For the methods before the development of numericals, people just using some classical trial functions based on polynomials or certain other bases to represent the functions. But now we have the new choice from neural networks. So the variation Monte Carlo with neural networks has becoming a very hot topic, starting from 2017 when Giuseppe Callio and the trial introduced the so-called neural network quantum states to represent the ground state for Ising systems, which is a discrete systems. And since then, there are tremendous research interest in applying machine learning in physical science. And in 2018, my collaborators and I developing a method based on the variational Monte Carlo for finding the ground states for real electron systems, just like the PDEs we were solving previously. And later on, there are a lot of researches going on from European demand group and other groups, and trying to find the numerical representation for electron wave functions. And I think it's still a very active area, and people are finding some real systems that neurotrocs can beat classical methods. So this is a very exciting area, and possibly can provide us new tools to understand the quantum chemistry or quantum physics systems. So that's one direction. Another direction I think promising is PDEs related to high dimensional probability. Okay, so suppose you have certain random stochastic dynamical systems formulated by in the form of SDE. So you have a lot of you can observe a lot of trajectories, and in order to know the densities in this real space, we have the famous Fokker-Planck equations describing the density at any time and at any location x. If you know the forward part and the diffusion part, but if your x is high dimensional, then you need naturally solve a high dimensional Fokker-Planck equation to understand or get the knowledge of this density space. So this is the important functions. This figure is just borrowed from a recent paper published in PNAS in this attempt using numerical-based method for solving the Fokker-Planck equation to get to understand to answer some questions in statistical mechanics. And a related topic you might have heard is the so-called scope-based diffusion or general modeling. Okay, there again, X denotes the data you want to manipulate. So if you want to deal with data generation with the image, again, the X can be huge, high dimensional with thousands of dimensions. And in order to do to implement the score-based diffusion, you need to find a numerical approximation to the score, and mathematically people can show that the score satisfying and HJB type equations. Okay, so this is another typical example of high dimensional PDEs. If we can solve this type of PDEs, then we have the full score information, and we can use that to generate high dimensional generate high dimensional samples of our interest. So I think both things are naturally connected to the numerical methods I'm talking about today based on backward stochastic differential equations. So because both type of problems and methods are connected to the stochastic differential equations, and we can do a lot of interplay on manipulation between the sampling part and optimization part in order to know better information of such high-dimensional probabilistic systems. Yeah, so this is the last slide. Some other topics that are also of interest in recent years, but I cannot cover today. First, when we need to solve optimal control problems or multi-agent games coming from game theory, we also need to solve certain high-dimensional Hamilton-Jacobi-Bellman equations. And for these kind of problems, deep learning algorithms is a useful tool. I have been, in the past years, I have been working in these directions for multiple projects. Second, if you go back to the low dimensional PDEs, there are still some complex low dimensional PDEs which are hard to solve in fluid dynamics, climate modeling, etc. So in that regime, okay, people are also considering using machine learning tools to solve to overcome certain computational difficulty, may not directly related to the physical space, the dimension of the physical space, but related to other unknown difficulties. Thirdly, another very hot topic nowadays is to trying to use deep learning to find solution operators for PDEs. So for operator, you are not solving a single PDE, but solving an operator related to a family of PDEs. Okay, so in such applications, even in the low dimensional physical space, the operator itself is still infinite dimensional. So it is again a very hard task, and now people are trying to find some networks to approximate this operator for fast evaluation. And thirdly, what I talk about today are all like a model-based methods. We assume we know the PDs, we want to find the exact solutions. But in certain cases, the PD itself may not be accurate, have with some unknown terms. So then you can think about use some data-driven methods to first infer the PD and then solve the solutions. So a combination of data-driven and the model-based methods will be of interest in that regard. And the last one is a topic in the reverse directions. Okay, all I talk about today previously is using machine learning tools to solve dynamical systems, but nowadays is another direction is also very active is to use dynamical systems or control perspective to study deep learning, so-called dynamical systems for deep learning. So yeah, so my collaborator Chen Xiao has done a lot of work in these directions. If you're interested, you can take a look. Yeah, so I will stop here. Thank you very much for interest. Mhm. Yeah. Okay, that's a very good question. Okay, if you take an abstract perspective, okay, they are all valid choice. They are different choice of using networks to approximating gradient of u, right? You can fix different discrete time t and only take x as input, or as you said, you can take t and x jointly as your input, or you can just approximate the u and take the gradient to represent the function u. So they are all valid. So in my original paper, I used separate formulation. It's purely due to the reason due to the performance of optimization. For PDs I tested, I find okay this like separated approximation of networks from with respect to gradient directly gives the best performance in terms of the loss functions. And but in other PDs, I have tried okay both formulations you just suggest are also valid choice. So I think it's more due to the optimization performance. And for different PDs, you do not have a prior idea which presentation is better facilitating easier optimization. You have to try and error. Yeah.
So in this variational formulation, you have this integral, right? Like you say, use Monte Carlo method. But your solution is changing. Do you change your evaluation point with a different u, or you fix the point you evaluate?
Yeah, that's a good question. So for this learning method, the calculation points can changing over the time. You don't need to stick with a fixed set of calculation points. So the typical practice in this kind of method, you just sample calculation points randomly over each batch, just like the SGD type algorithms. And so you can think this is one way to leading to better generalization. You do not overfit with a fixed set of calculation points.
Then the following question, following that is, we know that you say there's high probability when you generate this point, your converges to the true integral, right? But you have so many this sampling, there also your high probability you're not going to do well. I mean, when you sample this point, do these things will really approximate the true integral.
Yeah.
Right? Because there are many values you do. So how do you avoid some of the bad?
Yeah, that's a very good question. So I would say overall it's still open questions. So like for the physics informed network, people have found okay in a lot of cases, if you do not design a good sampling strategy of the collection points, okay, your solution will be very bad. So I would say generally it's open questions. Yeah. So yeah, certainly in high dimensional cases there can be difficult examples where sampling matters a lot. Okay. The reason it's not a big issue for the pedagogical PDs I talk about for BSD because, as I said, the fixed starting point is fixed. It's something we choose, and then we just need to sample points over that passes. So that issue is not so important for that type of PDEs. But in general, if you just want to deal with the integral, then apparently sampling the base measure for approximating the integral is important.
So have you tried any PDEs with oscillatory solutions? Like a Helmholtz equation?
I have not, but I know there are some works for that. Yeah. So or use some like multi-scale features to design better structure architectures to deal with the oscillatory feature of the waves.
Okay.
Yeah.
So there are some other people.
Yes, there are other people for that. Doing that.
So in the introduction, you present some dispersive equations, and the method could be applied to these equations. So I wonder, because there could be changes to do discretization for low regularity initial data, or also to have some structural preserving schemes, like in symplectic schemes, where in your process you could guarantee that at some point.
Sorry, I cannot hear you clearly. Can you say again?
And I'm saying that when you are considering discretization for dispersive equations, you may want to deal with low regularity initial data, which is quite a challenge. Also, you may want to preserve some symmetries like symplectic schemes, where in the process that you presented, I can actually act on that.
Okay, that's another good question. So yeah, I think it involves different aspects. So sometimes, for example, if you want to preserve the symmetry, if it's something you want direct approximate, you can try to design the networks itself to preserve the symmetry. Say if you know your solution should be rotational invariant with respect to the physical coordinates, then you can design a network to preserve that property, which means you can search in exact space, which is more efficient for problems. Yeah. Another thing is that if you have some other properties, like for example, if your dynamic system is like irreversible, or you want to guarantee certain conservation, it's more complicated. Yeah, that's why I said okay in the step 3, if you want to design, if you want to consider discretization of things, it's a new, like you can think, for example, for the symplectic systems, you need some special discretization to preserve that properties. So sometimes people are considering these kind of techniques. So yeah, so I think it's case by case.
So this is related, I guess, to the previous question. What are the usual architecture that you use for, besides, okay, sometimes you have to constrain them with symmetries and that, but just the basic, what kind of architecture?
Okay, so for the PDEs, for the examples I show here, I'm just using a standard feed-forward networks with skip connections. Yes, and nowadays for some large systems, people are, inspired by the success of large language models, people are also trying transformer type architectures, which is more powerful in terms of approximation, but which is also more expensive. Yeah, so for my works, okay, I have a philosophy that the network architecture itself should not be too sensitive to the final result, because here I'm just relying on its representation. I do not want a result algorithm that is very sensitive to the choice of an architecture. I hope as long as my network is representative enough with enough parameters, we can find good solutions.